We try to understand the features of the problem, the main characteristics of the problem, and now let's try to build a mathematical model that hopefully helps us in solving the problem. I recommend to you have the slides available, look at the graphical representation and the input data for the model so that you can compare it more easily. What to do? First of all, try to understand how is the solution to the transportation problem characterized. What do you think would be a good solution? What do you think would be an acceptable solution? How should a solution look like? What do you expect as a solution? What would you consider a solution? Does a solution include the name of the truck driver that is doing the delivery? Yes or no? Is this part of a good solution or not, if we have this problem? And then second, I would like you to try to identify a good solution on your own. So press pause and try to come up with a good solution that solves the transportation problem. This is important that you do this exercise so that you are more sensitive to the characteristics of this problem. Okay, let's move on. Assuming you've done the exercise, let's move on. We try to build a model, and the goal of our model, the idea of our model, is to support the management in decision making. Though the first question, and one of the most important, one of the most basic questions in all types of models is: what do we want to decide? Which decision do we want to support? And in this case, for the transportation problem, we decide about the transport quantity measured in cases of fish between each factory and each customer warehouse. How can we now represent these decisions in a mathematical model? We have to introduce some variables, and these variables, because they represent our decisions, are called decision variables. In this case, I introduce a variable with two indices, I and j. Though this variable represents a matrix, we have two indices I and j, and the index I indicates a factory. It can have one of the following values, f1, f2 and f3. To write this in formal notation, we write it in the following way. Our index I equals f1, f2, f3, meaning I can have one of these three values. On the other hand, index j indicates one of our four warehouses, so j can have the values either a or b or c or d. So now, how many decision variables do we actually have? We need a combination between each factory and each warehouse, so we have 3 times 4 warehouse decision variables. In total we have 12 decision variables. So xij represents the transport quantity from factory I to warehouse j for the following values of our indices. And then I give you one example. We have, for example, the decision variable x f2c equals 30. This means that we want to transport 30 cases from the factory f2 to the customer c. This is how we use the decision variables. Between the indexes, I here use a comma. Sometimes, if it's clear, we omit the comma. And of course, it's very important that we follow the same structure. So if you would write C first and F2 on the second position, this decision variable would not be defined. Even if it would be defined, then it would mean that we transport something from C to F2, which is not what we want to model here. Okay, first step, deciding which decisions we want to make and how to model these decisions. Second step, we want to make good decisions, so we need something that measures the consequences of our decisions. Here, the consequences of our decisions are related to transportation costs. And how do we calculate the transportation costs? In this setting, we know the transportation costs between each factory and each customer warehouse, and it depends on the number of cases that we want to transport. The number of cases we want to transport is measured by our decision variables. So have a look at your cost matrix or at the drawing. Going from factory F1 to customer A, which is Lulu, costs us 250 Baser for one case. And the number of cases of fish are measured by this decision variable. So if we should decide that we want to transport 10 cases of fish, then the value of XF1A would be 10, and it would be multiplied with 250 Baser. We have to do this for all the possible transport relations, for all the 12 possible transport relations, and add up all these costs. And then this gives us the transportation costs, the consequences of our decisions when we decide to transport something from a factory to a customer. And this is called an objective function. It measures the consequences of our decisions. That is how good our solution is. Though you already know now the decision variables as an important component of a model and the objective function. Let me give you an example for the values of, or for the outcome of an objective function. For example, we decided for the following values of our decision variables. From F1 to C, we transport 50 cases. From F3 to C, we transport minus 10 cases. From F3 to D, we transport 20 cases, and all the other transport relations are 0. No cases are transported. So if we now fill in the values of these decision variables into our objective function, we can easily calculate the following transportation costs, which are 37 reals. Though the consequences of this decision are costs for transportation of 37 reals. Now, of course, most of you will have stumbled about this thing, minus 10 cases. Does it make sense to transport minus 10 cases of fish? What would be the interpretation of this? On the other hand, you easily see in total we only transport 70 cases, so that means many of our retail customers of our warehouses do not get the number of cases they actually demand. So that means we need to extend our model to allow only, let's say, reasonable decisions. So in this context, it seems to make no sense to allow a transportation of a negative number of boxes. So we need to tell the model you're only allowed to use positive numbers for x. And we also need to add some more constraints to force the model to accept reasonable numbers that we think are really representing a solution. Yeah, the model itself does not know that -10 is a stupid decision. Yeah? We need to tell this model, and this is our task, to understand the logistics problem at hand and tell the model what are good solutions. If you later solve such a problem by means of software, you always need to find a way to explain the software what you want. And therefore you need to understand the logistics problem, and you need to be able to communicate with the software by means of model building. If you build the wrong model, the outcome will be wrong as well. So now how can we add these constraints? First of all, for all our 12 decision variables, we define that the values have to be 0 or bigger. Negative values are not allowed. So we use only non-negative decision variables. Then we have to add the following constraint. A fish processing factory should only ship everything it produces. Yeah, our contracts have a percentage defined with our customers, though we sell everything that we produce. That means if we produce 45 units, check your drawing. If we produce 45 units at factory 1, we need to make sure that all these 45 cases are shipped to our customers. How can we do this? We add up the decision variables for all the shipments from factory F1 to all our customers. Yeah? The index I is always F1, 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 F1 to the 4 different customers. And if we add up these decision variables, it should be 45. Of course, all these constraints have to hold together, though this constraint forces us to use numbers that are 0 or bigger, and this constraint forces us to use that the outflow of factory F1 equals 45 units. It cannot be bigger than 45, and it cannot be smaller than 45. An acceptable solution would be if F1A, if this decision variable would be 45, and all the others would be 0. Or we have F1A 5 and F1C 40, and the others 0. And this would fulfill this constraint. Of course, we have to model this type of constraint for each of our 3 factories. So for factory 1, we have this constraint. For factory F2 and F3, we have a similar constraint. For F2, we model everything that is going out of factory F2. You see, we have the index I set to F2 here. Okay, what happens if we only use this type of constraint? What is the problem when we only have these kind of constraints? What might happen? Try to think about it, and we solve it in the next video.